Disruptors and curious minds, CEOs, founders, book lovers. Welcome to the Thinking on Paper Book Club, where every week we explore the insight, the strategy, the ideas, and the secrets of books that have stood the test of time, books that will change your mind. Think of us as the antithesis of Blinkist and the 15-minute book summary. We are a 15-hour exploration. We're getting deep. This month we're reading Quantum Supremacy by Michio Kaku. We're on chapter 789. I want to start with a question for Jeremy. A question that we've been tiptoeing around for quite a while, I think now. And that question is, what drives life on this planet?
Whoa. Wow. What drives life on this planet?
And it's a clue. It's
quantum
7.
Yeah. Quantum processes, I think. I'm not going to answer. I'm not going to say the words that you want me to say. I'm going to riff on it. But to me, it's quantum processes, and it's things that we don't fully understand, but we're getting there. And actually, the rise of quantum computing has potential to help us figure more of this stuff out.
Okay. Well, I'll say it then, because it's written right here on page 116. What drives life on this planet is photosynthesis, the deceptively simple process by which plants convert carbon dioxide, sunlight, and water into sugar and oxygen, which, yeah, you were right. It's potentially a quantum process.
I was going to say the P word. So photosynthesis, man, like I'm going to start making shirts that like start promoting photosynthesis because
doesn't get the press it deserves.
It's amazing, right? Like, let's just talk about this. So there's a stat that I'm just looking at my notes over here. Photosynthesis creates 15,000 tons of biomass per second.
Per second.
Like, that's literally how the world is built, is off of this process that,
that's more junk than YouTube pumps out in a day.
Yeah, I mean, do we need to build a whole new storage industry just for the shit that photosynthesis builds? It's amazing, right? No, look at this quote. All right, photosynthesis. This quote talks about photosynthesis, end products of billions of years of totally random, chaotic chemical processes, and it developed these remarkable properties by chance. Is it by chance, or is it by quantum mechanical processes that we don't understand, right? It's pretty cool.
Yeah, it's very cool. And what I find really nice as well, and I hadn't thought about this, before the 1600s, we had no idea what it was and how it exists. That we thought that plants, to quote, ate the soil.
Right. Well, I mean, it's logical. They have these things that dip into the soil. You figure they're sucking up the soil, right? So here's another thing that we go in. This book is about quantum mechanics. This book is about quantum computing, but we're learning about these principles of nature along the way that I think is fascinating. So like just the idea in photosynthesis, photons create vibes. Like we talk about vibes and vibes being this like hippie thing. Vibes are real, dude. Like these vibrations are created on the leaf surface. They're called excitons. Excitons, right? And they travel across the leaf surface, right? And they move to this collection point where the exciton energy converts CO2 into oxygen. But how do the excitons know where to go? The path integral method, right? This idea that
are we back on Feynman?
We're back on Feynman again. Like, let's loop it back around. So like quantum mechanical understanding of all the possible paths to know the most efficient path, right?
Yeah. The excitation effectively picks the most efficient route from a quantum menu of possible paths. This requires that all possible states of the traveling particle be superposed in a single coherent quantum state for tenths of femtoseconds, and then it takes, when it all collapses, it's taken the path of least resistance. not sure that's what would be. Yeah.
So if you're listening to this, guys, and you're like, well, this book is supposed to be about quantum computing, like it makes so much sense to understand these natural processes to me, to now understand what the hell quantum computing is, right? And how it's applied. So I think it's rather entertaining to go through some of these things, right? So let me ask you a question, Mark. Why are plants green?
Light wavelength. When light, many sides of this special molecule, chlorophyll, absorbs red and blue light, but not green, which is scattered back into the environment. Hence, the green color of plants is due to the fact that green is not absorbed by them. If nature had created plants that absorb as much light as possible, plants would be black rather than green.
So everything with
chlorophyll.
You did know like the reason why though, the light reflection and stuff. It's pretty interesting, man.
Why sunsets and sunrises is all to do with refraction of light. Quantum computing, so people are watching. Oh, it's about quantum computing. What has the kind of plants got to do with quantum computing? And the reason is that we don't actually know how photosynthesis works. We think it's a quantum phenomenon. By using quantum computers, they hope that one day can actually explain photosynthesis, how it works, and then that idea can be transferred into, well, they use some examples, photovoltaic cells, so the solar age with perfect efficiency. If we can harness photosynthesis, we can go live on Mars and we can create photosynthesis in more extreme environments. On planet Earth, we can make crops grow where desertification or natural disasters or flooding or something has made the ground much more extreme, and where it used to work, it doesn't. There's many ways that we can harness this just by learning about photosynthesis on the quantum level.
Absolutely. And towards the end of this chapter, chapter 7, which is, greening the world, appropriately named, I'm going to read the last sentence that'll carry us into this next chapter. Unless do you have any more on greening the world chapter? Anything else that popped out that was interesting to you?
Again, it's the link between photosynthesis being a quantum process and quantum computers is that Mother Nature is. I don't want to get into breaking nitrogen and CO2, but essentially, Mother Nature is carrying out these changes at room temperature or whatever the temperature is outside. And so if we can work out that, then we can get quantum computers operating at room temperatures, not in these frozen tundra out in some huge lab in Google.
Yeah, and now that I kind of look back at this last couple of pages in Greening the World, the idea is, photosynthesis translating into like looking at how light could be used to split water into hydrogen and oxygen, right? So they're saying the hard part now is the final step, right? To find a cheap way to combine hydrogen with CO2 to create a whole new fuel source that's apparently better than a lot of the other sources that we have now to scale a lot of different things. And like you said, Mother Nature does it better than anybody. We'll go into it in the next chapter about how, bacteria are already doing that. We just don't know how they do it. If we know how they do it, we could produce a process to split the same thing to generate the result that we can harness, right? Humans love to harness shit. We got to wrap our arms around the shit so we could, point it towards things we care about, right?
Exactly.
All right. So last sentence here. Moving into from greening the world to feeding the planet. So ironically, the man who pioneered this last step, which is, we're going to be talking about fertilizer here, right? This last step, making it possible to feed billions of people and make modern civilization possible, is sometimes described not as one of the greatest scientists of all time, but actually as a war criminal. And we're going to be talking about Fritz Haber in this next chapter, which, ironically figured out this process that created fertilizer. But guess what? It also creates, these gases that were used back in the war to kill people, right? To kill massive amounts of people, right? So there's this
fertilizer bombs.
Yeah. off we go, feeding the planet.
So can you you explain the Haber-Bosch process?
Oh my gosh.
Do we need to? So I don't. You've spoken about the Haber-Bosch process before. I think you understand it. For me, is it about? So in nature, it's called fixing nitrogen,
Right.
but essentially, if I understand it correctly, on a very simplistic level, by fixing hydrogen, breaking it.
Exactly. You're trying to break this bond, right? So here I put some notes on the Haber-Bosch process. So what you do, super simple, guys, right? What you do is you heat nitrogen to 300 degrees Celsius and compress it by 200 to 300 times atmospheric pressure, and then you can break the bond and form ammonia. That's all you got to do, right? So again,
How peanuts don't do that, but peanut plants can do this, can't they?
That's where we're going. That's where we're going. So let's talk about this for a second, right? So the supply of nitrogen is plentiful.
80% of the universe.
80%, right? 80% of the air we breathe, right, is nitrogen in the atmosphere, right? So being able to harness that potential would be super powerful, right? But the challenge is it takes a lot of energy and a very specific process to do that. But man, the roots of beans and peanuts are already doing this better than our process that's 100 years old, right? So nature, again, it does things better, does things at room temperature. This is the importance of quantum computing, right? This quantum computing has the potential to unlock these little mysteries that could lead to massive, groundbreaking innovation. And I didn't know that before. Like quantum computing, when I first started learning about it, it was like, oh, it's just going to be a faster computer. You could just do shit faster. You could do things on two things instead of one, and degrees of things. But this is really big to unlock the power of nature in a lot of ways.
Well, yeah, it's it's taking those incredibly complex reactions of nature and trying to understand what's going on. And again, my knowledge of the Haber-Bosch process, didn't think I'd ever be on a podcast talking about that, is that it hasn't really evolved.
Yeah,
it hasn't really evolved because it's such a complex process. It's so hard to do because of the temperatures and the pressures involved that it hasn't ever evolved from that. And that's why we're still using it 100 years later. And we don't know how to make it more efficient, to improve on it, do we? And quantum computers will be able to take whatever elements and atoms are involved in that process and work out alternatives.
Here's another piece to quantum too that, and again, hi guys, I'm not a scientist or a computer scientist or a physicist or any of that. I'm a curious mind. So is Mark. Give us a little ease. We're literally unpacking this knowledge in real time, using each other, right? So if you hear something that you want to tweak with us or correct us or send us on a path, pop something in the comments. We'd love to hear from you. You will get credit in the next show. So catalysis.
They're a great band,
right? Metallica. So here's how I get my head around this, which is really, this could be really an interesting quantum thing, right? So catalysis is chemical reactions need a nudge. They need a little, it's a kind of a catalyst, catalysis, right? To get them going, right? So I'm going to butcher the pronunciation of this particular chemical, but nitrogenase is actually one of these catalysts that nudges the nitrogen fixing process. It's one of the nudges. So catalysts are essentially matchmakers, according to what Michio Kaku writes in this chapter. They're matchmakers of figuring out what to nudge in the chemical process. But guess what? Quantum matchmaking is tunneling.
Hold on, is ATP the catalyst? Sorry, what was adenosine triphosphate?
So this is
the nudge. Is that the?
I read that this nitrogenase was actually the nudge for nitrous fixing, or nitrogen fixing, nitrous fixing. Are we racing cars? Like, what are we doing here?
Okay,
we're getting over our skis in the science world. But suffice it to say, again, there is a natural process that we could further understand by applying quantum computing to it. So we talked through feeding the planet, right? There are some things going on that a lot of people, Google's CEO talks about, quantum computing may be able to improve the Haber process within a decade, right? That's pretty powerful in the next 10 years.
We tend to overestimate what we can achieve in the short term and underestimate what we can achieve in the long term. Change those windows to what I think that is a very ambitious prediction.
It's going to be interesting to see how quickly this stuff scales and goes. Like, because there might be a breakthrough that'll take us exponential, right? And we've been on this like short process, right? There's got to be, maybe there's a catalyst. What's the quantum chemical that?
What's the AI catalyst for the advancement of quantum? When does AGI? Let's say that we have a major breakthrough. This new open AI zero leads us to AGI within the next 2 years. AGI gets involved in this, goes, we don't need the Haber-Bosch process. I've got something different. Here we go.
Well, all right. So I read something recently that, I don't know if it was the recent release of ChatGPT, but there was a flag, I think, that came out about asking questions related to the Haber-Bosch process, because obviously that has potential for lethal applications as well as really good applications. So I think I remember seeing something out there related to, they're trying to put some guardrails on, helping people make stuff that they shouldn't be making. So
good luck with that. That's always worked historically, hasn't it?
It sure has.
We have learned.
We're learning right now, Mark. We're learning.
I meant the proverbial with the royal we, us, humanity, civilization, the powers that be. Chapter 9, energizing the world, batteries.
This was interesting. Again, like setting the stage for the why of quantum computing. I think all of these chapters have been like pointing to the why, understanding what in the past we need to be solving for, right? So to power the world, to energize the world, there's the gasoline thing, right?
Just on your point there, going back to the first part of book club on quantum supremacy, we did say, and Michio did say, and it says on the front of the book, we're solving the world's, humanity's big problems. We're talking about energy, feeding the world, photosynthesis, batteries. We're not talking about the simple things. These are the global, catastrophic, end of species questions we need to answer.
Yeah, and quantum computing seems to be the highest probability of getting us to, or the highest excitement level to get us some progress. So it's 1786.
Yeah, I like this.
You're in your lab. You've got some, for some reason or another, a couple of severed frog legs just sitting on your work.
So weird. Like what is going on? Like what was this guy doing?
They're just severed frog legs sitting there. And then somehow you figure out, you start rubbing a couple of things together and generating artificial electricity through friction. And then you decide to touch the frog legs with this rub metal. What do the frog legs do in your experiment, Mark?
I've read a question mark by here on this bit. It's like, what the fuck? Looking back, we see that the history of the battery has moved at a glacial pace across the centuries. In ancient times, it was well known that if one walked across a carpet, you might get an electric shock when touching a doorknob. Okay, we've all experienced that. But this was just a curiosity until history was made in 1786, when physicist Luigi Galvani was rubbing a piece of metal against the severed legs of a frog.
How do you get there? How do you get there? I mean, I'm sure there's a logical explanation of steps that
it was lunchtime. He had some French friends in. They were, he was preparing lunch. He was bored. Didn't understand what they were saying. Started rubbing a frog's leg.
Well, same reason that you think about there was one guy that stuffed a water mixture of malt and stuffed in a glass container and tucked it away for 2 months, and then decided to drink it for some reason, and it's why we can all enjoy pints right now. So some of this Yeah, some of this.
It's like the thing of eureka isn't the word of discovery. Eureka isn't something which moves the dial, is it? It's like you're in a lab and you don't go eureka, you go, that's weird. Hold on. And that's the sound of progress.
Yes. Well, what do we? Yeah. So it's like, were we talking about this? I don't know that it was in this book. Maybe we were talking about this in another form, but just the idea of like making new things and creativity. And for something to truly be creative, there has to be a novel use for it. There has to be an application for that thing. So you have the eureka. Oh, wow. I can make some frog legs bounce if I rub some metal sticks together and touch it. There's that piece. And there's like, okay, well, now what do we do with it? Right. Which we go. So here's what I found really interesting. And I always knew like gasoline did better than batteries, right? Just from a performance level. But, this stood out to me, gas having 12,000 watt hours per kilogram of energy, right? And battery having only 200 watt hours per kilogram of energy. And that's a pretty large difference. And I knew that. I knew there was a difference between batteries and gas, why electric cars only go 300 miles and tank of gas can do more than that. But seeing those numbers was pretty jarring for me. What about you?
Oh, well, you were on Team Ford. I really like the story at the beginning of the chapter about Edison and Ford, Thomas Edison and Henry Ford, and how they were friends. I didn't know they were friends. And
they used to hang out at his place in Fort Myers.
Yeah, well, okay. Yeah, Ford idolized Edison in his early years. They became friends. They started going on holidays together, and they started making bets, gambling men, betting on which energy source would power the future. Edison favored the electric battery while Ford believed in gasoline. They made some bets. And the idea of having a gas station every few blocks was considered preposterous by Edison. That didn't age well.
Right. That's right. Well, you have one or the other, right? You either have charging stations or gas stations. Like what? And gas stations edged out.
Big time. But maybe not.
So again, here's the theme again, guys, is some of these innovations, especially related to chemical processes, are currently completed just through brute force, trial and error over time. So like to brutally simplify this, like if you have like, I don't know, 5 different chemicals, right, together, and you want to figure out if this chemical can do this thing, you combine them each at a time. So you combine one with 2, and then one with 3, and then one with 4, and then one with 5, and then, so on and so forth, to all the way down the process, till you just brute force run through all these options, where what quantum computing is proposing that it can do is change that to a simulation of doing the path integral, right? And doing it all at once, figuring out which one works. So, I mean, when you think about that as the foundation of the potential in the process of quantum computing, if that's true, holy shitballs.
That was more than a brutal simplification. That was a beautiful simplification. I like it. Almost as beautiful as the Nobel Prize in chemistry that was given for lithium ion batteries to a chemist called John B. Goodenough.
Really? His last name was Goodenough?
John B. Goodenough. Yeah, he won it with Stanley Whittington and Akira Yoshino, but John B. Goodenough, what a name. But yeah, so lithium ion batteries. So it's lithium air batteries. We're talking about the next stage on from that. We're talking about my knowledge of lithium air batteries stops there.
Well, let's go back to lithium ion batteries, right? So this guy won the Nobel Prize, right, for this, and again, probably through this brute force of just trying different shit and landing on one that works. You're just grinding, right? You're grinding. But guess what? Like, as good as lithium ion batteries are, they, according to this book, they still only have 1% of the energy stored in gasoline.
Yeah. Nothing.
Yep.
You can see, you can understand why the automotive industry is so interested in quantum computing, can't you? By the way, Automotive Link, yesterday's show live on Spotify, was about the automotive industry. But yeah, you can see when current batteries are so inefficient compared to fossil fuels, and when there is this almost inevitability of the non-use of fossil fuels at some point in the future, having batteries which are more than 1% efficient comparatively is urgent.
Well, yeah, and you're starting to see these, for lack of a better term, kind of these centers of excellence around quantum computing in the automotive industry. Back as early as 2015, Daimler created the Quantum Computing Initiative, right, to kind of stay ahead of some of the things that can be done. Mercedes-Benz Research and Development, North America, they've been trying to figure out some of the quantum stuff for good reason. And let's get tangible with it, right? They Michio Kaku had actually created some really good lists in here as to what's the shortcut why to these guys are leaning into this, right? So we talked about creating better batteries, right? So batteries are a chemical process. That's a quantum process. Quantum computers, quantum processes, that ties up together, right? Also determining the best places to install electrical charging stations, right? So maybe that's a little path integral kind of thing, like where we lay these things out. All the pieces and parts that go into a car, pretty complex, pretty complicated, both Julio Tino, if you're listening, complicated and complex, right? So that both of those, figuring out a way to purchase those the best way, more of an efficiency mode. And then aerodynamics and safety. Safety, listen to the show we had this week with our great guest, Barry, talking about safety in cars.
Did you get enough on the lithium air batteries to know if electrical charging stations could become redundant in the future? If you've got a lithium air battery that's non-sealed and using air to activate reactions in it, maybe you wouldn't even need stations to charge. Maybe it would just be always like a dynamo, always charging.
Well, the energy density of lithium air to lithium ion is 10 times, right? Lithium air is 10 times the energy density, which is good, which is better, but it's still not, a massive solve. But you got a ton of battery companies trying to figure this stuff out. It'd be interesting to watch them. You got like Super Battery, Nawa, let's see, talking about cobalt batteries too. Like, it's basically like what in nature can we use to harness and make things that can store energy that's accessible and renewable, right? Those are all natural processes. So, man, if you just have quantum process or quantum mechanical or quantum computing to run those simulations, holy cow, we could get there, instead of 30 years, maybe we get there in 10 years.
10 seconds. Right then.
That feels like a good, go ahead.
It feels like a nice place to stop. I'm going to read the last couple of sentences from this for next week's show, a little teaser. We now turn to how quantum computers can create a revolution in medicine. The fountain of youth, instead of being a fabled wellspring of eternal life, might turn out to be a quantum computer. Next week, quantum medicine.